Well, we did a lot with differentiating functions of more than one variable in the last chapter, and we're going to learn that you can also integrate functions of more than one variable in this chapter.
That's the loveliest thing I've ever heard.
I'm glad you think that's great. So, yeah, if we integrated like a partial derivative with respect to x of x and y, and notice the dx here, that's very important to see that dx, then you would, like, here's an example of one, integral of 2xy plus y squared dx. You treat the y and this y squared just like they're constants. So, in other words, how would I integrate a constant times 2x? Well, I'd say it's x squared. It's actually 2x squared over 2, and the 2's cancel, so it's x squared times this constant y, x squared times a constant y. And the integral of a constant dx is just the constant times x, so plus y x squared. Now here's something that you might find interesting. Then plus some constant, which is the constant of integration, but keeping in mind, since we're integrating with respect to x, if we differentiated, that could be any function of y. So instead of calling it c, a constant, I'm calling it c of y, meaning that could be any function of y, because now if you differentiated this function with respect to x, see, you get 2xy, see the integrand, plus, we're integrating with respect to x, so plus y squared, plus 0 if we differentiate with respect to x. So we do in fact get our integrand whatever this function of y is. So that's something to be noted. And here's an example of one like this. And by the way, this is going to be something that's different for you, that the limits of integration can be functions of the other variable. When I'm integrating with respect to x, the limits of integration could be functions of y. And so this is kind of the same problem as the last one. I have the same integrand, but now when I integrate with respect to x, of course, remember this was my answer. But instead of putting in nothing, actually, it was just plus c. But now I'm going to actually put in these functions for x. So here's our answer to our integration, right? Since this is a definite integral, I won't have a constant. So I just have this integrand, see it right here, evaluated first when x equals y squared, and secondly, and subtract when x equals 1 minus y. So first this x squared, well, x is replaced with y squared, so it's going to be y squared squared times this y, plus y squared times this x, which is y squared, so plus y squared times y squared, and then minus, this is like, evaluated at y squared, and then we evaluate it also at 1 minus y. So replace x squared with 1 minus y, we get 1 minus y squared times this y, plus this y squared times this x, which is replaced with 1 minus y. And of course this can be simplified, but this is just an algebraic exercise to simplify this into this y to the 5th plus y to the 4th minus y squared. What happens is, looks like I must have a negative y, no, this would actually give me a positive y cubed here and a negative y cubed there. Something like that must be happening. Either that or I have a mistake, which is entirely possible. No, this is actually the negative one here, and this one will actually be the positive one, because the negative here and this negative would make it positive, this y cubed. So they'll cancel each other out, and we do get this answer without a y cubed term. And I hope you find that interesting. But the procedure for evaluating such a definite integral is this. When you have the function which is represented as a partial derivative with respect to x dx, and the x limits go from g1 of y to g2 of y, then you find f of xy, which means integrate as if y was a constant, and then we get that answer for our indefinite integral. But then this is a definite integral, so then we put in x equals g1 and x equals g2, as the constant. So then we'll evaluate it and we'll say f of, remember, x equals g2, so we'll replace all x's with whatever g2 is, and then minus f of g1y, so we'll replace all the x's with g1 and see what that is. Vice versa, if we have a partial derivative with respect to y as an integrand, so we're integrating that with respect to y, then we'll get the function of two variables, f of x, y, and then our limits of integration would be y goes from g1 of x to g2 of x, so our function would be f of x, y, but I'm going to replace all the y's with g2 of x, minus f of x g2, but I'm going to, g1 of x, but I'm going to replace, actually that would be f of x, y, but I'm going to replace all the y's with g1 of x and subtract. So we'll do an example in the next video.